what we started up with last time was redox, right? As the name suggests, the topic in itself covers the entire topic. It's reduction and oxidation both. So here when we talk about reduction and oxidation, I'll just quickly summarize last time's class. We are doing redox reactions, in which we are basically going to talk about the reduction as well as the oxidation part. It is that science which involves oxidation as well as reduction, and we did different types in this particular case. One were the intermolecular, and the other one was the intramolecular redox reactions. You know, intermolecular was the one in which two species from two compounds were getting either oxidized and reduced simultaneously, and in intra, both the elements, two different elements from the same compound, were getting oxidized and reduced. Then we had, in this case, we did talk of the disproportionation reactions also, which we also did talk about when we were doing the other classification, in which we do the combination, displacement, what else do you have? The opposite of combination is decomposition, in which your molecule gets dissociated into different compounds. So in disproportionation also we had done one of the examples, like we have Cl2 plus 2OH minus, that gives ClO minus plus Cl minus plus water. So here you talk about the same species getting oxidized as well as reduced, and you all now know how to calculate the oxidation number. In this case the oxidation number is 0 here. Here it becomes X minus 2 is equal to minus 1, so that becomes equal to plus 1, and here this is minus 1. So you see that chlorine is going from 0 to plus 1, and it's going from 0 to minus 1. Alright, and then we also did another classification, that is we talked about the direct redox reaction and the indirect one. Alright, direct is the one in which your reduction or oxidation are carried out in the same container, very good, and the indirect is the one in which they are carried out in different containers. And then we had discussed the differences between oxidation and reduction. What was those? Oxidation basically refers to loss of electrons, and whenever you talk of one from your previous classes point of view, you did talk of oxidation as addition of oxygen, removal of hydrogen, or addition of an electronegative element and removal of an electropositive element. Whatever I said for oxidation is just the opposite for reduction. So here the major thing that we looked on now from 11th grade point of view was that we do talk about the loss of electron, and here we talk about the gain of electrons, right? This was the major catch, and this completes the chapter. So what we had here, we had taken up many examples last time. Then after talking about the oxidation and reduction, we also did understand as to what is the difference between an oxidant, which is also oxidizing agent, and what is the difference between a reductant or a reducing agent. Remember that a reducing agent will be the one that will reduce others but oxidize itself. So that means it will have a self-oxidizing power much higher. So in that case I would say that it will reduce other species and oxidize itself, right? You just remember one and the other one is like automatically remembered. So what is oxidizing agent going to do? It will oxidize other species and reduce itself, right? This is what it is going to do. Then after that we did talk about some important oxidants also, and I gave you a clue that whenever you have to talk about the oxidants or the oxidizing agents, they are generally those molecules in which your element is generally in the highest possible oxidation state, so that it cannot go further high in oxidation number. So what will it do? It will reduce itself, and if it will reduce itself, it will oxidize others. So it will then act as a good oxidizing agent. Clear with it? And we had taken up examples like K2Cr2O7, and then we can have KClO4 or HClO4, you can have a KMnO4, H2SO4, and so on. The catch here is that you look at the central atom, which is like in this case you talk about chromium, and it will be in, check out the oxidation state, K is in plus 1 oxidation state, K is in +1 oxidation state, so you will have +2 here for K, plus 2x minus 14, because oxygen is here as -2, so what you have is equal to 0, and your x will be equal to 6. So for chromium, +6 is the highest possible state. So we know it very clearly that chromium cannot go beyond 6, but it can always come down to +3 or a lower oxidation state. So then in that case we can say that here it has full chances of behaving as an oxidizing agent, no other chance at all. Then when we talk about HClO4 also, similarly, just I've taken up 2 examples from the many that we've done. What is this? This is +1 plus x minus 8 is equal to 0. Why -8? +1 for H, for oxygen it will be -8 minus 2 into 4, so that becomes -8, so x becomes equal to 7, which is the highest possible state. You know, as it is for fluorine, chlorine, bromine, iodine, they are the halogens, so they have 7 valence electrons. So either they can gain one to complete their octet, or they can expand it to the max that they can extend their valency to +7. That's the maximum where they can just empty up their outermost shell. So that is another thing. Alright, then you can have the oxides of metals and non-metals also behaving as oxidizing agents. Like for example, you talk about CrO3. It is also a good oxidizing agent, and then you can also have oxidizing agent like MgO can also act as an oxidizing agent. Carbon dioxide can also act as an oxidizing agent at times to provide the substance with an additional oxygen. Okay? Oxidizing, reducing substances, I don't think there should be any discrepancy here. And when we talk about the important reductants, I did mention that reductants will be generally those which have chances of going to a higher oxidation number. For example, if I talk of NaH, here my hydrogen is already in which state? -1 oxidation state, because this is the hydride. We had written some set of rules for deciding onto the oxidation numbers last time. So here, because this is hydride, it will have an oxidation state of -1, and if this is -1, it will have full chances of going to either 0 or to +1. So here it has chances of oxidizing itself, means it will act as a reducing agent, because it can if it can oxidize itself, then it can reduce others. Alright. Then we had also looked at how to find out the equivalent weight. I did give you an example to find out the equivalent weight, right? That was of a substance which is undergoing a redox reaction. Like for example, if I talk about, I'm just reminding you of this particular reaction that we did in the last class. If we have H3PO3, and that's forming 3H3PO4 plus PH3. So what will we do? The equivalent weight of the oxidant or the reductant, this will be the oxidant or the reductant, in this case is disproportionation. I'll just come to the question. Here it can either act as an oxidant or reductant. The equivalent weight will be equal to the sum of the 2 half reactions. You will check out the 2 half reactions which are like possible in this case. Here you check out what is the oxidation state for phosphorus. Check it out here and check it out here. Quickly do it. Work out the oxidation states. Why phosphorus does not exist in P2 form like oxygen, since both are in the same period? Phosphorus is in, sorry, I'll just come to this, I'm just looking at the question. The doubt that has come up is why phosphorus does not exist in P2 form like that of O2. Let me tell you, the oxygen group is usse tipo. Have you forgotten? You remember? Yes. What is oxygen? Oxygen, sulfur, selenium, tellurium, polonium. Phosphorus belongs to nitrogen. So phosphorus actually belongs to the nitrogen group. So first of all, you have some kind of ambiguity in this to understand that phosphorus does not belong to the, oh okay, you say it's belonging to the same period. So it belongs to the same period. No, it doesn't belong to the same period also, because it is nitrogen. Then you have phosphorus belongs to the nitrogen group. The first of the nitrogen family is nitrogen. The first of the oxygen family is oxygen. So first of all, there is a discrepancy here in the question itself. And why doesn't it exist as a P2 form? Now, whenever you talk of a molecule to be existent in a diatomic state, there are certain factors which need to be followed up. Let's go back. thankfully I have done these topics with you, so I will be able to understand that what I've done with you, so accordingly I'll explain. In phosphorus you are talking about P2 formation, whereas in case of nitrogen you have N2 formation, and in case of O2 also, oxygen also, you have an O2 formation. What happens when you go from the first period to the second period? There is a availability of extra which orbitals? D orbitals, right? Because in the topmost period, I told you the very first of all the elements of any group, they do not have availability of vacant D orbitals. So now here you have chances of expansion of your chances of expansion of your bonding part. So because you have availability of more free orbitals, so therefore the catenation tendency also increases. So P does not exist at P2, but rather it exists as P4. And you have white phosphorus, and then you have yellow phosphorus, and you have different allotropes of phosphorus depending upon the structure. Okay, now why displacement reaction always occurs in solution? Displacement reaction always occur in solution. Let me just finish this question and come to your question of displacement reaction. See both the questions. Okay, so here what were the oxidation states? Tell me. 3, 5, minus 3. Now let me just check out the change. What is the change in the oxidation number here? It's going, phosphorus is going from +3 to +2. So there is a change of 2 electrons, and as you're going from +3 to -3, there is a change of how many electrons? 6 electrons. So 6 electrons. So remember that in this case the equivalent weight of H3PO4 will be equal to the equivalent weight now of your molecule will be equal to molecular weight divided by 2, because the molar mass divided by 2 plus the molar mass divided by 6, because we'll take into account the change in the electron or the oxidation numbers here in this case. So this is an important question that I had taken up even last time. Then there were other reactions that we did talk about. Let's talk about them. Since somebody had asked for the displacement reactions, I did tell you that for the displacement reactions, you have a metal which is more active. This is something that you've done before also. A metal which is more active will replace the metal which is less active in the activity series. This is what you have done. Displacement reactions, all right. So like for example, I talk of CuSO4 plus Fe. This is the reaction that you generally do. So let's take it up. That gives you FeSO4 plus, there is something wrong in this question, in the equation that I've put on the board. What is wrong with it should be Fe2 plus, because it's replacing your Cu2 plus, all right, and then here you will have Cu2 plus. Now the question was, try and answer it yourself. I said that there was something wrong in the equation that I put on the board. I wrote that this was simply Fe. Fe means simply metal add करा. Metal तो as it is हाथ में भी रख सकते हैं, ठीक है, metal हाथ में भी रख सकते हैं. Question ये है कि ये solution में ही क्यों reaction होगा फिर? Metal हाथ में रखो, copper sulfate यहाँ रखो, फिर उसको yes. Now because we have ions which exist only in again let's come back to our favorite molecule. What is our favorite molecule? NaCl. Whenever we talk of NaCl, it's like something that we are like all familiar with. So when we talk of NaCl, we have Na plus and Cl minus. As it is, हाथ में नमक पकड़ोगे तो you will have, and you pass current through it, nothing will happen, right? But the moment you add salt to water, what will happen? It will become Na plus and Cl minus. And because it will become Na plus and Cl minus, ions will exist in solution. The moment you pass an electric current, there will be a, do not try it at home. So it is like it will immediately create a spark, right? It will immediately create a spark. So you do not have to actually check it out, but I'm telling you, and I've already told you that all salts are strong electrolytes. This is a thumb rule that you do not have to forget. मतलब ये salt है क्योंकि इसमें Cu2 plus है और SO4 minus है. The moment you will put it in water, it will exist as Cu2 plus and SO4 minus. But what will happen now, because Fe2 plus is more reactive than Cu2 plus, it will replace Cu2 plus to form FeSO4 plus U2 plus, which produces a change in color. And then in the displacement reactions, what we have, I did tell you the activity series. What was that? PCS, magenta, and then you have hydrogen, copper, silver, gold, platinum. No, copper, silver, gold, platinum. Just check it out. It may be wrong also from my this thing. So it is. Just check out the series. It should be potassium. Then you have calcium, sodium, magnesium, aluminium, zinc, iron, nickel, tin, lead, hydrogen, copper, silver, gold, platinum. Right? It should be like that. And any metal which is placed above will replace the metal which is placed below. Clear with that? And then we did talk about the other redox reactions also, like in case of combination reactions, you have decomposition reactions, you have displacement reactions, and you talk about disproportionation reactions. Okay, then we had taken up the important points for determination of the oxidation number. Something which are to be remembered. Some of the important points that I generally remember is like alkali metals will always be like +1. Alkaline earth metals will always be +2. Your oxygen in the normal form will be like -2. But if it is in a peroxide form, it will be -1. If it is in a superoxide form, it will be -1/2. It will be -1/2 and something like that. And you can all remember those points to find out the oxidation state. And I had given you some examples last time, out of which one of the doubts that we got stuck with was Na2S4O6. So find it out for sulfur again. This is like a very simple example. Do not go through your notes, rather do it yourself. And another one that I gave you was to find it out for Keros acid. Find out the oxidation state of sulfur in Na2S4O6 and also find it out in case of Keros acid. What is your Keros acid? It is H2SO5. This is also something that I had taken up before. It is H2SO5. H2SO5. So you will need the structure of H2SO5. I am taking these two only up for revision because these two had come up as doubts also. So and for H2SO5 you need the structure also. It will be HOSOOH and you have sulfur forming 2 oxygen bonds like here. Here for sulfur it is for fair Na2S, that is like 2.5. 5/2 or 10/4. And what about this one? This is for the oxidation state of sulfur in Na2S4O6. What about this one? Agree? Why? Because if you know the structure, many a times in the examination you will be given the structure. This is a peroxide linkage. This is a peroxide linkage. So if you're given the structure at that particular point in time only, it should actually click you immediately that if your oxygen is just lying as it is, it will be in -2 oxidation state. Again for OH, you know that here it will again be in -2 oxidation state, but because this is a peroxide linkage, it will be -1 and -1. Again for your hydrogen it is +1 and +1, and then you can find it out. Alright, then it turns out to be 6. And one example that I gave you was for NH4NO3, where you will be talking about separate oxidation numbers rather than taking 2x. I told you that for salt cases where there is a repetition of the element, where you have N in NH4 and N in NO3. So here in this case you will be talking about N in the oxidation number of N in NH4 plus, so you can easily find out x plus 4 is equal to +1, so that will be -3. And for NO3, then it will be NO3 minus, so x minus 6 is equal to -1 plus 5. Okay? So in salt cases you will have to find it out separately. Some of the examples that we've taken up already. Then we did talk about the stock notations, which is nothing but you decide on to the oxidation number and then just assign a Roman number to it. Okay, and then we moved on to the balancing of the reactions. That was something that we had touched upon last time, is meant for today. We have the balancing of the reactions. There are now a number of methods that are mentioned in your books also. One of them is an ion electron method. Remember that the ion electron method is the same as the half reaction method. ठीक है, मतलब you separate out your reduction half reaction and you separate out your oxidation half reaction, and then you balance it out accordingly. And the other method that you have is the oxidation number method, which is also very interesting. Let's check it out one by one. I am just repeating now the ion electron method, which is very simple and can be related to the redox. Or let me talk about the oxidation number method first. Ion electron method is something that we had done towards the end of the last class also. So we'll quickly talk about it after talking about the oxidation number method. Let's talk about the oxidation number method first. Alright, let me just take up an example and explain. Okay. Attention onto the board now. And then I'll give you questions to practice. Oxidation number method. As the name suggests, you will have to write down the oxidation number for each of the elements. Okay, let me just give you a reaction. ठीक है, Mg, reaction लिख लो. Mg plus you have HNO3 giving Mg NO3 whole twice plus N2O plus H2O. Alright. First of all, I have given you the equation in this case. In many of the cases, you will not be given the equation at all. So the basic thing is like whatever, if it is a combination reaction, displacement reaction, now you know how to write down the formulae of the compounds. Just add your reagents, starting reagents. मान लो दो reactant दे रखे हैं, magnesium. Had this question been magnesium reacts with nitric acid to give you magnesium nitrate along with nitric oxide. Nitrogen oxide can be anything, it can be NO, it can be anything, so it will be given in specific as nitric oxide. So what you have is, you have dinitrogen oxide, so, and water. Alright, water may or may not be given because it comes in the balancing many a times. So this data is like sufficient to you. First write down the skeletal equation. After writing down the skeletal equation, what is the next thing that you will be writing down is the oxidation number in each case. So write down the oxidation number. Oxidation number for magnesium is 0, plus 1 for hydrogen, plus 5 for nitrogen. In fact, you will be finding out for nitrogen here using hydrogen oxygen. Oxygen is minus 2, यहाँ पे magnesium is plus 2. Then for your nitrate, you have nitrogen in plus 5, oxygen in minus 2. And then you have nitrogen is minus 1. And oxygen in minus 2. Alright, let's check out the change in the oxidation state. What is the change here? It is changing from 0 to 2, so that's like 2 electrons. And your nitrogen is changing from plus 5 to minus 1, right? Yeah. Here you will have 2x minus 2 is equal to 0. So x will be equal to plus 1. Right? So here you will have a change of 4 electrons. Then what will be the change here? Right? It will be a change of 4 electrons then. Now if I balance out the nitrogens, see here, if I check out only this nitrogen part, then you check out this is 2 nitrogens and here I have only 1 nitrogen. So let me just put it 2 and then find out the change. Because at least let me have the balance of those oxidation states. So because this is N2 and I am talking about, if I say that this is going from plus 5 to plus 1, but each of the nitrogens is possessing plus 1. It's not a single nitrogen. So let's put a 2. Now look at the change in the oxidation number. It is now plus 10 for the nitrogen. And now you can say it is plus 2. Plus 1 for each nitrogen. Is getting the point? Because oxidation number is a little twisty. The other one is very simple. You just put hydrogens here and water there and just balance it out. I repeat it again. Here, फर्स्ट ऑफ ऑल वी आर असाइनिंग द ऑक्सीडेशन नंबर, यहाँ तक सिंपल है. उसके बाद when we are moving from one state to another state, now we realize what is getting oxidized. Magnesium is going from 0 to +2. So magnesium is acting as a reductant because it is oxidizing itself, so it is acting as a reductant. And here your nitrogen is going from +5 to +1 generally, and then we work it out by balancing the number of nitrogens here in this case, because our focus is on nitrogen, the central atom. ठीक है, तो 2 नाइट्रोजन है, यहाँ पे हमने इसको 2 कर दिया. जब 2 कर दिया तो व्हाट इज द चेंज इन द नंबर ऑफ इलेक्ट्रॉन्स नाउ? इट्स गोइंग फ्रॉम 10 to 2, so that means a change of 8 electrons. Got it? And now that means here 10 to 2 means it's -8 electrons, here it is +2 electrons, or the other way around. If you write this reaction, इसको मैं कंफ्यूज ज़्यादा नहीं करना चाहती. What we have to do is we have to balance the number of electrons in both the cases. ये वाले इलेक्ट्रॉन्स को बैलेंस करना है. सो इफ आई एम टॉकिंग अबाउट Mg इज गोइंग फ्रॉम Mg to Mg2 प्लस 2 इलेक्ट्रॉन्स. ठीक है, एंड N का क्या हो रहा है? N इज गोइंग फ्रॉम से +10 ऑक्सीडेशन स्टेट टू +2 ऑक्सीडेशन स्टेट. सो इट विल बी -8 on the other side. So -8 electrons. So do you get it? We're just trying to understand as to what is the change. So here that means if I multiply this 2 with 4, then that becomes equivalent. So what I'll do in the next step is, let me just see what they've done. Equalize the total increase or decrease in the oxidation number. Equalize the total increase or decrease in the oxidation number. How will I equalize? This is 8 electrons. So this will have to be multiplied with 4. And if I multiply this 4, so this 4 will come with this magnesium and it will come with this. Alright, with this magnesium nitrate. So with both the species you will be actually using the 4 as you will be multiplying it with 4. So the net equation now becomes 4Mg plus 2HNO3 giving 4MgNO3 whole twice, right, plus N2O plus, now you balance out your water. It may or may not be given in the question. Check out the number of hydrogens here on the left hand side. On the left hand side we have only 2 hydrogens, but we need to balance it out with the extra nitrates also. Is that so? So in that case, just check out the nitrogens on the left hand side. Here you have 4 2s are 8, right? You will be actually multiplying it with 5, but then here you have, in total you have 8 plus 2 10. So here if you multiply this with 5, then you will have to take 5 nitrates again here. I repeat it again. Here when you balance your hydrogens and oxygen, balance hydrogen and oxygen, what you get is you will take 4Mg plus you have first of all let's balance out the hydrogens. How will you balance out hydrogens? You have 4 hydrogens here, and then you add, if you take 5 hydrogens here because you want to make it 10, so then in that case check out the extra hydrogens which are there. You will have 8H plus extra. If you take 5 water on this side, then you will have 8H plus because 2 hydrogens were already there. And now you work out for the nitrate part of it. If you work out for the nitrate part of it, what you have is you take the spectator, add the spectator ions. Last time I told you the significance of the spectator ions is that they do not participate in the main reaction, but they are like, they can be added on either side to balance the overall reaction. So when we add the spectator ions, the equation then becomes equal to 8H plus 4Mg plus 2HNO3 plus, because you have 8H plus, so those pluses have to be balanced with NO3 minus. So how will they be balanced? You will have 8NO3 minus giving 4M had, it's like a common sense, the starting reagent only had our HNO3. So the only ion which can be used to balance out your H plus will be NO3 minus. Let's try out more examples of oxidation number method to avoid any kind of a confusion. Let me just see.